So why don't we get started? Today is mostly what I usually do is a week before the experiment, I'll go over the experiment, or if it's an activity, we'll go over the activity. Of course, if you guys have any questions on previous material, you can certainly ask me. What you see is, since I'm in my office, I forgot a cable. So I have to use 3 computers so that you guys can see what I'm doing. But I think it'll be okay, because I think that at least this screen that I'm pointing at, I can bend and you guys can see what I'm doing in terms of the technique, and then follow along some of the instruments that I'm going to be using. So today, let me just go over, and first of all, let me remind you that these things are being recorded. And if you have problems with that, please let me know, because I don't want to infringe on your privacy. Of course, you can always turn off your video and rename yourself. But I think what I promise the rest of the class is that these things will be recorded so that you guys can go back and preview them as at your leisure. So the other thing that you could do is you could also make sure that you write something in the chat if you have any questions, or just unmic yourself. Okay, so yeah, I'm in my office and I forgot a few cables that will not allow me to connect to my iPad, but I think I've worked it out so that you can see what I'm doing. So if you look at experiment number 2, and the best way to look at that is to actually go, because there's a few modifications that I need to state, is that we're not doing a marble. We found cubes this semester, so you guys can be able to do that. And it's not a metallic cube, it's actually these things, and it's going to be different colors. Okay, and the thing about these is that these are actually the template for dice. So, but it's okay, because it serves the function of what we need to do. Okay, so these are the cubes that you guys should have. I think there's a white, a black, a blue, and a green. You guys would have one of those. So that's the only modification that I believe is going on in terms of the write-up, and I'll make sure that I change those wording in the write-up when you actually see it in Canvas. So let me just go back here and share my Canvas screen, and then I'll go back and you guys can take a look at that. So if you go to your course, if you go to the module, you guys will see that there is the lab manual right there, and it's this one right here, says Lab Manual 2021 Spring, and it's sort of the other clean flip page program that I was using. They wanted $200, so I found a free one. Okay, so this is it right here. There's advertisement, but if you actually do larger view, you don't have to worry and see about the advertisement that's there. But if you click down here, it'll actually do like your pages, or you can of course do this, and it looks like it's pages. So we're at experiment number 2, which is right here, and you can zoom in. Okay, and tells you right here that we do have a cube, we do have a string, but then in the wording I forgot to change that. So let me zoom in again. And so this is it. So in the first part of this particular direction, we're going to be measuring temperature. The second part is mass, third part is length, and the last part is volume. So let me just go through these sequentially so that you guys are on the same page. Okay, so it's a program in Mac that it's basically a photo booth. So let me go ahead and start with temperature. That's the first reading. What you guys will be doing is you guys will take a beaker, one of your beakers, fill it with water and let it sit for a while. Okay, then you're taking your thermometer, and let me zoom in on the thermometer, because I want you guys to pay attention to the thermometer. You guys know that the bottom is 20, the top is 10, 0. It's right here. Okay, in terms of that, 0, 10. So this is minus 10 right here. This is minus 20. Now, as we talked about the thermometer last week, the way you are going to read this is based on the calibration mark. Now, if you look at the 20 right here, and you look at the 30, there are 10 lines in between. So each hash mark or each tick mark is 1 degrees Celsius. This is a Celsius scale. So if delta is 1 degree, then that means you can read it to the 10th of a degree, always 1 decimal point over. Okay, so when you read this thermometer, and everybody has the same type of thermometer, you better be reading it to the 10th of degree, because that's the precision of your thermometers. Okay, and it's based on the hash marks that you see right here. Each small increment is 1 degree. So if it's 1 degree, then you can read it 1 more digit over. Okay, if this right here was, if you take a look at that reading, the red line is right almost to the halfway mark. The halfway mark is 25. So below that, it's past 24, but not quite 25. Then you got to figure out how far along that, and you have to be at you have to make sure that you are eye level, because notice how it changes when I change the angle. So you got to be at eye level with that alcohol. And then you have to figure out between the 24 and the 25 mark, what percent is it up to the 25? If it's 40%, then it's 24.4. If it's 50%, then it's 24.5, because the 24 is a certain number, but the 0.4, the 0.5 is your uncertainty because you're estimating that. So by putting a 0.4, 0.5, you guys are telling me that the precision of this thermometer is 1 degree. Okay, that that the tick marks are 1 degree and that the precision is 0.1. That's what I meant. Okay, so the very last digit that you write down, if this was 24.4, the very last digit that you write down in your data is the uncertainty. It's the degree of the precision. If you're writing it to the 10th, that means that your degree of precision is plus or minus 0.1. But suppose this was finer. Suppose that the delta was 0.1, then that means that your increment, I mean your precision, if delta is 0.1, if each hash mark was 0.1 degrees, then you're going to be reading it to the 100th, 2 digits past the decimal. And that means that your error is going to be plus or minus 0.01. 2 digits past the decimal is to the 100th, because your very last digit, let's say that I'm reading it as 24.01, your very last digit is to the 100th, then your error is also to the 100th. It's plus or minus 0.01, because that very last digit that you write down, the rightmost digit, is your uncertainty. You're estimating that. So hopefully that's clear, okay? Because that's the take-home message that all of you are going to be needing to use in this experiment, as well as your lab practical, okay? So what you want to do is you want to fill it with water, and it doesn't really matter to me what the temperature is. It's going to be varied, but whether you get this question correct or not is whether you are reading the temperature. Well, first of all, water, room temperature water, is not going to be minus 20 or minus 10 or even 3 degrees. Okay, it's going to have a range somewhere between 10 and maybe 25. So I know that that's the range, but the most important thing that you guys need to remember is how many digits am I writing down based on that measurement. That's what I'm looking for. It's got to be in the ballpark, okay? But more importantly, it's got to have the correct precision, because everyone has the same thermometer. Everyone has a thermometer that has hash mark at 1 degree. Everyone should be reading temperatures to the 10th of a degree, and make sure you write your units. Okay, so that's the first part. The next part of this, if you take a look at the lab manual, you can like have your browser, is length. And what you want to do is you want to measure your height, the length of your shoes, and the circumference of a 400 milliliter beaker. Now, what you need to remember is that when you measure your height and you're basically just going to a wall, you probably, let me just change this, go up against a wall, make a mark, get the mark, and from the floor up, you're reading it, okay? And it says to read it to centimeters. And I know that your ruler that they gave you is definitely not long enough to measure your height, but hey, you guys can like stack it up or something, okay? But the main important thing about the ruler is that these things, you have to read the metric system because we are in a science class. If you start reading the inches and the feet, that's automatically incorrect. All your measurements should be using the metric system. That's what this lab's about, okay? So the first one is to measure your height in centimeters. The next one's to measure your shoe length. Now I have my, okay, Zoris, as we call it here. And what you can do is you can either mark it on a piece of paper, okay? Just mark it on a piece of paper and then measure that, okay? And again, shoe length is going to have, it's going to vary, but I know the range, okay? Some people might have very, very long feet, but they're not going to have feet that are going to be like 24 inches or something that's really huge, okay? You got to be a giant for that. At the same time, you can't be that small either because then you're a baby. So it's going to be in a range that I know is going to be reasonable. And what you guys are going to be doing is basically measuring that. So again, it's to determine, make sure that you guys know how to read measuring device. I'll talk to you guys about the precision of ruler shortly. In terms of a beaker, what you guys want to do for the length of a beaker is you can't take your ruler, and some people have done this and they basically try to wrap it, and that's because these things are not bendable. But what you can do is you can take a string, and that's what the string's there for. You can wrap it around, and where it intersects, let me see if I have a pen here. Where it intersects, you can mark, okay? You can mark that right there where it intersects. Just make one line. Now what you can do is you can unroll it, find where that is in your and so you can see that I have a mark here and a mark here. All I gotta do is stretch it out and then measure that length, okay? And all 400 milliliter beakers are going to have approximately the same circumference. We're measuring the circumference. This is the best way to measure circumference rather than try and wrap your ruler around it. Now let's take a look at the ruler because that it's kind of important. I think I talked about this in our last discussion, but I want to really make sure that we stress this. We're measuring length now. Now, if you take a look at the ruler, you'll see that it's a metric, first of all. And again, I apologize that it's backwards, but you guys can see it's 1, 2, 3, 4, all the way to about 15. This is a 15 centimeter ruler, okay? Now, each line, long line is 1 centimeter, right? This right here, let me see if I have a pen. This right here is 1, this right here is 2, and so on. This right here is 0, and notice that the 0 is not quite at the end. So never measure anything using the butt of the ruler because you're going to be offset. Always measure something in the middle and then realize that that is your 0 mark. So when I measure this line, this length, okay, what I'm going to do is I'm not going to take, let me show you this, and let me mark this so that it's clear where my lines are. You might have to darken it. Okay, here's 1 and here's 2. Okay, here's 1 right here, and here's the second one right over there. Now, when I measure this thing, I'm not going to take my ruler. Best thing to do is actually just write it in a piece of paper and make the end match the line, because notice that that end is offset. Okay, it's offset. So the line is the 0 mark. The side here is the negative, probably 1 millimeter. So what I want to do is I could either make sure it lines up with that line, or I can move it to the 1 centimeter and then mark 15. But really, when I mark this 15, that's actually 14. And then do the same thing here, all the way to this line right here, and then I would just have to estimate it. And you guys can write in the ruler, because you can certainly do that, or again, if it's in a piece of paper, you can certainly do that. But again, that's one thing I want you guys to know, is that the edge is not 0. That line is 0. The best technique is to start at the 1, where you know that that's the start line, and then remember that if you go from 1 to 2, that's actually 1 centimeter. If you go from 1 to 3, that's actually 2 centimeters. You just have to remember that. Don't like measure something from 1 and then go out here to about 3.4 and say that oh, it's 3.4 centimeters, when really it's only 2.4 centimeters, because you didn't start at the 0 mark. Okay, so I just want you to remember that. Now let's take a look at this ruler. If you take a look at the ruler, there are 10 divisions, hash mark, between the 1 and the 2. That means that these right here are 0.1 centimeters. From here, you can see my finger now, okay, to, good thing I groomed it so that you don't see the dirt. But if you go from here to here, that's 0.1 centimeter, right? That's 0.1 centimeter. If you go from here to here, that's 0.1 centimeter. So now you know that your delta, that is the division between each line, is 0.1. That means that you can actually read your ruler to the 100th of a centimeter, because if your delta is 0.1, then if the measurement falls between these two hash mark, then you have to estimate again how far to the next line it is. And so if you take a look, and I'm zooming in real closely, let me just mark this so that you guys can see it. Okay, let's say I have that. Now you can see. Okay, so let's say I'm measuring something from the edge, and this is 1, this is 2, and you can see that that wasn't meant to be right on the 4. Okay, that would be misleading. I want to make sure that it's in between. Okay, I'll make sure it's in between. It's difficult because yeah, there, that's better. It's difficult because these lines are so small. But let's take a look at this. You can see that this is 2 over here, and this is 4 right here, but not quite to 5. But that line where I start at the very top, is it 50% to the 5? Is it 70% to the 5? Is it 80% to the 5? If it's like 80% to the 5, and that's what I will say, then I would say it's 2.48. Okay, and notice 2.48. 2 digits past the decimal. That means I'm reading it to the 100th of a place. Okay, 2 digits past. And your error, because that 8 is an estimate, that's what I said, that 8 is an estimate, it's plus or minus 0.01. The very last digit to the right as you write these measurements is the one you're guessing. That's your uncertainty. That's your uncertainty. Okay, because I could have easily read this as 2.49 or 2.47. See how that last digit changed? It could have been 0.47, 0.48, 0.49. That last digit varies. And so that's the uncertain digit that I'm estimating. Therefore, it's plus or minus 0.01, because that's the one that varies. That's your uncertainty. And it's based again on the delta, the length of that hash mark from here to here. That is 0.1. okay, centimeters. That means you can read it one more past that decimal, 0.01. So that's how you would read the length. And let me remind you that, yeah, when you measure your height, it's going to be very estimate. It's going to be very vague because it's a very long length, but you still, because you're still using the same ruler, be measuring it. You better be measuring it to the 100th of a centimeter. If you just say, oh yeah, I'm about 620 centimeters, then you're going to be wrong because you're not reading it to the precision of that measuring device. Don't just estimate it, actually read it based on the precision of the measuring device. That's what the take-home message of this experiment is to be able to look at your instrument that you are using, figure out the degree of precision, again, based on the delta of the hash mark, and then write your measurement based on that degree of precision. That's the key. So that takes care of the length. Let's take a look at the oops. Take a look at, let's see. I think we need to do the mass. Okay. Maybe I forgot. One is the first one is the temperature. The second one is the length. The middle one's the mass. Let's take a look at the mass. Okay. And the mass is based on your digital scale. Make sure that when you turn on your digital scale, that it's reading grams. Okay. And you know it's grams because right here along this line, it should say G. If it doesn't say G, then you're not in the correct unit. Okay. The neat thing about these digital scale is that you can tare it, T-A-R-E, and that zeroes the balance. Okay. So what you will end up doing is, in order to protect the balance, you want to put a weighing boat. And the weighing boat's going to have some mass. But if you tear it, now it zeroes everything. So as if the weighing boat did not have mass. And then what you can do, of course, is you can just put the object on the weighing boat, and the mass that digital scale reads is the mass of that object. You don't have to subtract the mass of the weighing boat. Okay, make sure that it reads it in grams. Make sure it reads it in grams because that's important. So according to the directions, you're going to take not the marble, but the cube. Okay, you're going to take the cube. You're going to make sure that the scale is correct. You're going to tear it, let it stabilize for a moment. Okay, and then put the cube there and let it stabilize. And then what you guys are going to do is just write the whole thing, because the precision of these scales is the whole reading on the display. It's the whole reading. But look at the display. If I press it a little bit, notice the last few digits. Okay. Let me just see. I got to turn this around so I can see what's going on. At least for me, let me put a different object that way. We put a different object. Let's say I put this one. Okay, so I'm going to let this stabilize. And the reason why I want to press it a little bit, because I want to see the last digit to the right. I want to see how it fluctuates, because that's my degree of precision. Some scales going to fluctuate every 0.05. That means that your error is every plus or minus 0.05, because it doesn't read a 4, it doesn't read a 3, it goes from 0 to 5 to 0 to 5. In this particular scale, I think we got you a better scale. It actually reads that very rightmost digit actually fluctuates between 0 and 9. So that means that the error in these scales are going to be to the 100th. Again, 2 digits over is the 100th place. It's going to be to the 100th of a gram plus or minus 0.01. Because as you press these things, they actually fluctuate between 0, 1, 2, 3. It doesn't go from 0, 0.00 to 0.05. If you have one of these scales that we used to have in the before, these things had an error plus or minus 0.05. But the scales that you guys have, if you have these scales, actually have better precision because their precision's 0.01 grams. Okay, so when you put your cube here, make sure that you zero the weighing boat. Put the cube there. You're just going to write everything. And if you want, you can say, oh yeah, the error on these things plus or minus 0.01. Okay, so the first one is the cube. The next one's a 100 milliliter beaker. And the reason why we did 100 milliliter is because that's the smallest beaker that you have. And in the past, what I asked students to do was weigh their 450 mil, and that was past the capacity of the scale. So you're just weighing your 100 mil beaker. Again, you can put the weighing boat, you can tear it, and then just put the beaker on top. And this one will read you again a bigger mass, but again, the same precision. The precision will always be the same, plus or minus 0.01, plus or minus 0.1, if you're using the same measuring device. We're using the same measuring device when we measure the cube. We're using the same measuring device when we're measuring the beaker. So your error is going to be the same, plus or minus 0.01 grams. Okay? It's not going to change unless you change your measuring device. The mass will be different, but the uncertainty, the precision of your measurement is still to the 100th of a gram because the measuring device that you guys are using is the same. So let that be a lesson to you guys. You guys are going to be using the ruler throughout this course. So whenever you take a measurement and you're reading it, or whenever you take a scale, look back to experiment 2, because that's how many digits, that's the uncertainty of your measurement, because it's the same measuring device that you are using for those later experiment, and it better not change. If in this experiment you say that the mass is plus or minus 0.01, and then you go to an experiment down the line, let's say experiment number 5 or 6, that's the MOLAB, and you only give me a mass of say 1.3, then you've already forgotten about experiment number 2, because if we're using the same scale, it better be 1.3 something. It's got to be to the 100th of a gram, not a 10th of a gram. Okay, that's why I said that experiment number 2 is really important, because you guys are looking at the degree of precision for the equipment that you guys are using in this class. So that takes care of mass. Oh, there's also the 10 Mil Grad Cylinder. 10 Mil Grad Cylinder is the same thing. Yeah, you can tear it. You don't really need a weighing boat for these things. You can just put it on here and then just read it. So these are the things that you guys can measure. And I think the capacity of these scales is about, let me just press this. It's not quite reaching 200 grams. So anything above that, it basically overshoots it. And so you can't really measure things that are really heavy, because these things have limitations. Okay. The one thing about scales is that the more that they can read, the less precision they have. So if this thing could read, say, 1,000 to 2,000 grams, then the degree of precision is going to be less than a tenth. It might be less than 100th. It might be only a tenth. If you want this thing to read like 1,000, 2,000 grams and have a degree of precision to the 100th, then you're going to have to pay big bucks. Okay, you're going to have to pay big bucks, because the capacity and the precision are something that has to be built into the scale. Capacity means that it can handle large weight. Precision means that it can distinguish between small measurements. So anyway, that's the scale. Now the last one. Okay, the last one is the volumes, and the volumes are going to be, I think it says that you guys have graduated cylinder. Yes, it's plastic, but it still has the same degree of precision. You guys have a 100 Mil Grad Cylinder. Okay, you guys, I believe, have a 50 Mil Grad Cylinder, and you guys have a 10 Mil Grad cylinder. Okay, let me just make sure that that's the case in the lab manual. I believe that's the case right here. Yeah, it's a 10, 50, and 100. Let's take a look at the 100 first. I'm going to skip the 50 because I want you guys to figure that on your own. Okay. I'm not going to give you all the answers in this review, but I'll give you most of the answers. Now, what I want to do is I probably, because these things are transparent, I'm going to put a tube in here so that you guys can see the increment marks. Okay. And so I got to put some sort of contrasting agent in here so that you guys can see this. Okay, I think you guys can see that now. Take a look at this right here. You will see that this thing goes from 0 all the way to the bottom. You can actually remove this, I believe. It goes from 0 all the way to 100. Okay, all the way to 100. Now, this is a true 0. This is a true 0. These things were made so that when you start filling water in here, there's no negative volume. These things are true 0. From here to here, that's 10 milliliters. From here to here, that's 20. Okay, I think yellow works better. Okay, yeah, yellow's better contrast. So if you take a look at the lines between 90 and 100, there are 10 of those. That means that from here to here, that's 91, 92, 93, 94, 95, halfway mark, all the way to 100. So that means now you know delta. Delta is 1 milliliter. If this is 90 and the next line is there's 10 lines in between, then that means that each line is 1 milliliter. Now you know delta is 1. That means that you can read one digit over, you can read it to the 10th of a milliliter. Okay, so let's take a look at this. What I'm going to do is I'm going to pretend that this is the height. This is the volume that I'm going to be reading. So I'm just going to drop this in here so that's below the mark. And now I can look at that. Okay, so let's take a look at, first of all, you got to make sure that when you read this thing, it's got to be at eye level. You notice how you can see the back in this tube. So this is actually a good demonstration, because if you read it at an angle, you're going to have something called parallax error, and you're not going to be reading the true volume. You actually got to read it at eye level so that the back and the front are the same height or the same level that you're reading. Because if you tilt it, again, you're going, because water's transparent, you're going to be reading it differently. If you tilt it forward or tilt it back, you're going to have something called parallax error. So you got to read it at eye level. You actually have to bring the graduated cylinder to your eye so that it's at eye level. Okay, when you do that, then you're going to be reading it correctly. Now, let's take a look at this. Let's take a look at that. Okay, so you can see that it's 91, 92, but not quite to 93. Okay, take a look at that. Let me see if I can just sit this down so it's stable. Oops, so it's stable. What happened to, what happened? It went in the back. Okay, let me just sit this down right here. And again, I apologize. I got to tilt this a little bit so that it's the same. Let me see if I can't even bring this forward closer like that. So what you can see is that it's past 92, not quite 93. Again, you have to figure out how far past 92 is it towards 93? Is it the halfway? Is it 40%? Is it 60%? I say it's halfway. Okay, so that means that this particular reading is 92.5 milliliters, plus or minus 0.1. Because delta, each hash mark is 1 milliliter, you're reading it to the 10th of a milliliter. Okay, so, and it's going to vary depending, and in this particular case, all you're doing is filling up a graduated cylinder and reading it. And I'm not asking you to fill it up to a specific volume. I'm asking you just to fill a graduated cylinder and then read it. And then in the direction that I actually tell you, to the nearest 0.1. Okay, I actually tell you if you read the directions, it's 0.1, which because the graduate cylinder that you guys have has hash marks delta of 1 milliliter. That means you're reading it to 0.1. I also tell you what it is for the 50 mil grad cylinder. And the reason why the 50 mil grad cylinder is 0.05 is because the 50 mil grad cylinder, if you take a look at it, let me remove this and put this in so that you guys can see, is because if you look at delta in the 50 mil grad cylinder, you will see that delta is sort of weird. Okay, this is 40 and this is 45. Okay, that means that this is 40, 41. Actually, so each one is 5 milliliters. And again, the delta is 1 milliliters. I don't think you guys have the, take a look at your graduated cylinder, because I don't know if you have the same type of graduated cylinder I have, okay, where it has, if you do, then the delta here, even though there's a halfway mark and it gives you that, the delta here is 1 milliliter, which means it has the same degree of precision as your 100 mil graduated cylinder. Again, because if you look at each line is 1 milliliter. If this is 40 right here, and that's 5 up here, then that's 41. Okay, delta determines the precision. If your 50 mil grad cylinder has a delta of 1, then you're reading it again to 0.1 milliliter. That's why I should take a photo of that, because I want to see what your graduate cylinder is. Anyway, let's move on. Let's take a look at your 10 mil grad cylinder. This one's a little bit more precise, and that's because it's measuring a smaller volume. So the degree of precision is actually going to be higher. If you take a look at that right there, you see the 8, the 9, and the 10. But between the 9 and 10, there are 10 lines. Each delta, therefore, is 0.1. If this is 9 right here, and this is 10, then that line between the 9 and that next mark is 9.1. That means delta is 0.1, which means you're reading it not to the 10th, but to the 100th, one more digit past 0.1. So let me see if I can put something in here, and you guys can bend this. Again, as a demonstration, so that you guys can see how this thing works. Okay. Let's put this in here and then measure that. That's not going to work. The reason why it's not going to work is because the lines, well, I knew these tweezers were good for something. Let's measure the bottom. Okay, let's measure the bottom. I think that'll work too. So if you take a look at the bottom, and that's not good because it's not even. I should just put water. That might be better. Should have thought about that earlier. Okay, so let's take a look at water. And this actually is a good idea, because if you take a look at water, you see how it curves? It curves up. That's called the meniscus. That's called the meniscus. Okay, it curves up. That's called the meniscus. And the problem is that water sticks to glass. That means that what it tries to do is it maximize its surface area to the glass. That's why it's curved up. If you fill it all the way to the top, it'll actually curve down because it's sticking to the glass. But because it's below the very top, it's going to curve down, because then it can maximize its adhesion to the glass surface. The glass has oxygen, water has oxygen, it likes to hydrogen bond to glass. Anyway, the way you read this is you want to go at eye level again, always at eye level, and you read the bottom of the meniscus, the very bottom. Not the top, not the middle, but the bottom of the meniscus. That's the true volume. And again, if you tilt this, you'll see that it can vary. See how I tilt it? And it looks like the volume is higher than true. And if I tilt it the other way, it's actually lower than true. That's why you got to read it at eye level. And I'm trying to make this at the same eye level as the camera. Okay. Now that you get it at eye level, then you can read this thing. And there's going to be two scales on the graduated cylinder. One goes from the top to the bottom, the other goes from the bottom to the top. Don't read it from the top to the bottom. Okay, read it from the bottom to the top because you're reading the volume that's in your graduated cylinder. So I'm not going to read this as 2 point something because that's the wrong scale. I'm going to go over here and say it's going to be 8 something because that's the right scale because the amount of water in here is 8 plus milliliters. Now, what I want to do again is I want to zoom in and you want to look at the bottom. And if you look at the very bottom, and I apologize, I need a better, what you can do, of course, is get a black background. We do this in lab. Apologize that I can't teach you guys in lab, but you use a black background so you can see and contrast and don't have the glare. So in this particular case, you can see that this is 8 down here, this is 8 down here, and that's 8.5, okay? That's why you got to be able to read this. So if you read this, it's going to be between, if you just look at that very bottom, it's 8.6, but not quite 8.7, okay? It's 8.6, past 8.6, but not quite 8.7. Again, you have to estimate that last digit. I'm so sorry, I'm shaking. I can't be a surgeon, but that's the estimate. Like 8.65 milliliters. Again, you're reading it to the 100th of a milliliter. The reading is not so much important as the degree of precision. You better put some 2 digits past the decimal, otherwise it'll be wrong. Because I could have changed this volume to something else, okay? Like this. It'll be a different volume, and all of you are not going to have the same volume here, but everyone's using the same graduated cylinder, so everyone's going to have the same degree of precision. This one's 6.1. Again, you want to use a contrasting, not quite to 0.2, 6.1, maybe 7, maybe 8. That's the important reading. You're reading it 2 digits past the decimal. For the 10 Mil Grad cylinder. For the 100 Mil Grad cylinder, you have a different degree of precision. Okay. So that's basically it. The last one, the very last step here is something that you will do as well in your lab practical. You guys are all going to be measuring temperature. You're all going to see, I'm already telling you what's in your lab practical. You guys are going to be measuring temperature. You guys are going to be measuring length. You're going to be measuring volume. You're also going to be measuring density. So you run this experiment as if you were doing a pre-trial for your lab practical, okay? And when you get it back and I grade it and I tell you, oh, you're not reading it to the correct precision, remember that, because come midterm and final, you basically do it the same. You guys, by the time you go to microbiology, by the time you become a nurse, you got to be able to read your instrument based on the way the precision of that instrument. That's why this is so important in terms of your SLO. Let me take a look at the lab manual real quick, just to make sure that I've covered everything. We've covered that. We've covered. Okay, the last one, part 2, determine the density and identify an unknown. So what you guys are going to be doing is you guys are going to be taking this right here. I don't know if the lab tech gave you a metal cube. If they gave you a metal cube, don't use that. It's too small. So your reading is going to be somewhat small. Just use this cube right here. It could be plastic, it could be acrylic. Anyway, I give you a list at the very bottom of different material that this cube can be made of. Okay, what you want to do is you already got the mass. The next thing you want to do is take your graduated cylinder, take this, fill it to the 20, doesn't actually have to be 20, it could be 30, it doesn't really matter. Okay, but try and make sure that you read it to 20 point. Remember, these things have a degree of precision to 0.1 milliliters. So when you fill it to the 20 mark, it's 20.0. It's not just 20, or maybe it's 20.5, but it better be read to the 100th of a milliliter. What you want to do next is you want to take your cube, and actually before you do that, you do this, you measure the volume twice. One is actually measuring the volume using the ruler. And again, you want to make sure that you take your ruler, use the centimeter scale, and put it right at the edge, not at the end, but right around maybe the 1 or 2 mark, and then read that length. Okay, read that length. And because this is a cube, they're going to be the same all the way around. They're going to be the same. The length, the width, and the height is going to be important. And you want to read it to centimeter. Like in this particular case, if you, let me see if I can do this over here. Okay, I'm just going to butt this up right there. Again, you guys can do this better because you guys will be doing this at your own. I'm just kind of demonstrating it, and I got shaky hands because I had too much coffee. But here you can see it goes to 1, and this is not 2 point something. This is 1 point something because I'm starting at the 1 line. I didn't start at the edge. Okay, so if you make a mistake and say, oh yeah, this is about 2.45 centimeters, you're going to be off in your density. Why? Because it didn't start here. So that's not really 2. That's only 1.4 something, because between the 1 and the 2, that's 1 centimeter, and it's not quite halfway through. So make sure that you remember that. You're going to be measuring the sides of these things, and the width, the length times the height in centimeter is a cubic centimeter. A cubic centimeter is a milliliter. Okay, a cubic centimeter is a milliliter, cc. If you're a nurse, you know that they're going to inject you with 10 cc. 10 cc is 10 cubic centimeter. 10 cc is 10 milliliters. Okay. Now, what you guys are going to do is you're going to take one of your graduated cylinder, probably the 100, fill it to some value, and then you're going to put it in. And the displacement of the water is actually the true volume. Based on the degree of the precision of the graduated cylinder, the water is going to rise. And as long as it's submerged, and all these should be submerged, that difference between the initial and the final is the volume by displacement. The volume by displacement of that cube. So now you have 2 volumes. One is by geometry. One's by geometry. The other one is by water displacement. So that's basically what you have in this last part. You're measuring 2 volumes, and you're going to get 2 densities. And densities better be close to each other. They're not going to be exact, because the degree of precision for one type of measurement and another type of measurements are going to be different. So one of them is going to give you a bigger error, but at least both of them should be about the same ballpark. Okay, should be the same ballpark. And that's what you guys will be doing in this last part, where it says volume by displacement, volume by direct measurements, and then based on the density, it's the mass. The mass is going to be the same, right? The mass is not going to change as long as it's dry. Make sure it's dry, because if it's wet and you weigh it, then the mass is going to be different. But make sure it's dry. Just take some chem wipes or tissue paper and make sure it's dry, so that there's no water residual that would add to the mass. But you could just measure it once and then use it for your 2 calculation. Then you will get the density. The density is the mass in grams over the volume in milliliters, or volume in cc's, because cc's and milliliters are the same. Then you can use the chart that is in this lab manual and see which material is actually closest to the density you calculate. Then you can tell me what that material is. Is it acrylic? Is it glass Pyrex? Is it granite? Is it cellulose acetate? at least it'll be close to one of those. And these things, because they sink in water, better have a density of greater than 1. Because if it has a density less than 1, it's actually going to be floating in water. Okay, it's actually going to be floating in water because water has a density of 1. Anything that has a greater density will fall to the bottom. Anything with a lower density will float on top. That's why oil floats over water, because the density of oil is actually less than the density of water. Okay, so that's your experiment. Okay, that's your experiment. Let me just go back to Canvas and let me show you what needs to be done. So let me switch gears here and go back to Canvas, and let me talk to you about what you guys need to file. Because unlike experiment 1, where there's only one report you need to turn in, this has several parts. So let me go ahead and do that. And let me go over here and let me do this. Okay, so I'm going to go to Canvas, and you find, of course, experiment number 2 right here under the modules, and we are right here. So this first part is just the lab manual. Okay, these are the equipment that you would be using. You can see that I have my calculator, I got my scale. You don't have a marble, you got this cube that we have, and these are our graduated cylinders. Okay, so that first part, if you want to see again a closer look on how we measure, these were my earlier lecture on the degree of precision. It's basically what we just talked about right now. So these are some lectures that I've had on, because again, you guys need to know about reading measuring device correctly. So let me get out of here. Oops. Let me hide that guy. I don't want to see him. Let's go back to module. Okay, let's go back to module. Let's go back to experiment number 2. Here, this is a pre-lab. Now the pre-lab is what you guys will turn in, and there's a submit at the upper right button, but fill this out. Okay, it sort of primes you. That's what the pre-labs are supposed to do. It primes you for the type of experiment you're doing, the type of calculations you are doing. These are not hard. When you're measuring things scientifically, you're using the metric system. Okay, and the metric system uses prefix to indicate magnitude. Like if I have a millimeters, a milli is 1/1000th of a meter, or 1/1000th of whatever measuring you have. If I have a gigameter, that's 1,000,000 of what increment I have. Okay, so the prefix tells you the size of that particular measurement. So in this particular case, let me try and explain it to you this way. I have a meter stick. I don't have one here, but you guys, oops, you guys can see me. Okay, there. A meter stick's about a yard. If I take that meter stick and I break it up to 10 pieces, each one of those increment is a decimeter. Decimeter means 1/10. If I take that meter stick and break it up to 100 parts, then each one of those parts, because there's 100 of them, is a centimeter. Notice the centimeter is smaller than a meter. It takes 100 centimeters to equal 1 meter. If I take that meter stick and break it up to 1,000 parts, then one of those small parts is a millimeter. It takes 1,000 millimeters to equal 1 meter. So when we go from deci to centi to milli to micro to nano, we're getting smaller. So it takes more micrometers to equal 1 meter. In fact, it takes 1,000,000. It takes 1,000,000,000 nanometers, 1 billion nanometers, we can't even see that, to equal 1 meter. So right here in this first thing that we see, hopefully you guys will see that. Yeah, here, that's 1 times 10 to the 9th nanometer. That's 1 billion nanometers. 10 to the 9th and n are are basically telling you that I've got a billion of these small pieces. A nanometer is very, very small, but I have a billion of them. What does that equal to? Hey, that equals a meter. Okay. A lot of students in the past have been frustrated with this. It's not to frustrate you, it's kind of to show you that these questions are not difficult if you think about it. Look at the next one. It says micrometers. A micrometer is 1/1,000,000th, very small, 1/1,000,000. But if you have a million of them, isn't that just 1 meter? So again, these things can be intimidating if you don't understand the concepts of the metric system. Okay, if you don't understand the concept of metric system. Now look at this, 1 kilometer. Kilo means 1,000. Okay, you need 1,000 meters to equal 1 kilometer. So that, again, this is going the other way. This is going the other way. You need many of the meters to equal one of these. Again, it's to get you guys to understand the metric system. Here, you're just converting the different temperatures. Here, you're using the different mass. And make sure that when you guys use the conversion factor, use the conversion factor that is in the lab manual. In the lab manual, if you go to the lab manual right here, at the very end, you will find this thing. Let me see if I can't do this. Let me see if I can just go over here. Okay, right there. Okay, let me blow this up. Use that. That way we're all consistent. We're all consistent. Use that conversion factor. Okay, so that's what you want to use in these right here when you answer these questions. Use the ones in the lab manual, and then once you complete that, take a photo and then submit it. Let's move on to the next one. The next one is your experiment. So let me go back and go to assignment. It's very difficult navigating Canvas. I'm realizing every time I go back, you don't really get back to the mod. You actually have to click on module so you can find that again and then go to the data sheet. So this is where, if you click on this is where you start filling in your data. The magnitude is the number, and make sure you have the correct degree of precision. And then the unit is whatever unit you're using. Because we are in a science class, everything better be in the metric system, okay? So that's what you're doing. You're doing the temperature, the mass, and again, we're not doing the marble, just cross that out and say cube, okay? And then here, I need to make sure that you understand that.
The magnitude is the measurement?
What? The magnitude is the number. Okay. Is the number that you have. The unit is the meaning of that number. Whenever you take a measurement, there's always two components. The size, the magnitude, how big it is, and then the meaning of that number. If I just say, okay, I weigh 70, you would be looking at me and be puzzled because you're used to pounds. But if I say I weigh 70 kilograms, then you have it in context. Okay, so you can't just quote a number. You have to quote the number, which is the magnitude, and the unit to give context to that. If you don't write the unit, then someone might misinterpret that number. That's why it needs meaning. Okay, let me tell you about this right here. Scientific calculator. You have a calculator. I don't want you to weigh it. I want you to take a look at it, maybe compare it to the glass beaker, okay, and say, okay, they're about the same height. And my beaker is about 150 grams. So this calculator is a little bit lighter, maybe it's 120 grams. But don't say it's 120.56. And the reason why you can't say it's 120.56, even though your scale said that this was 150.47, is because it's an estimate. When you're estimating it, you're going to have, your error is going to be larger, plus or minus 10 grams, plus or minus 1 gram. So you're not going to be saying that because I'm estimating this calculator, it's 120.87. It's going to be giving you more information. It's like looking up at the person that's coming down the street and say, okay, you're young. You look like you go to college. I'm going to estimate that you're about 21 years old and 5 months and 3 days and 6 hours. You can't do that because you're guessing. Same thing when you're guessing the mass. You can't say that this is 120.56. You can say it's about 110 grams, 100, maybe 98 grams, but you can't give it more precision than what your estimate is. And the reason why we have this right here is, again, to get you guys used to the metric system. If I say, okay, how much would this be in pounds? You say, oh, I know what a pound feels like. This is way less than a pound. It's probably about a third of a pound, okay? And that's because you guys are used to the pound scale because you use it in your everyday life. We want you guys to be used to the metric scale. So that's why you estimate. The length of your calculator, that's the second one. Okay, I know what my ruler looks like. Okay, I know what my ruler looks like. I know what my calculator looks like. This is less than 15 centimeters. I say it's about maybe 11 centimeters, but I'm not going to say it's 11.56. If you put 0.56, again, you're being more precise than your estimate. Your estimate has probably an error of plus or minus 1 centimeter, if that. Okay, so again, estimates are basically rough guesses of what you think these things are: the mass, the length, and the volume. You take a test tube. I think you guys have a test tube in your glass kit. Okay. I think you have various. I think you have test tube in your kit from KLM. This one's a bigger test tube. If you fill it to the top, the smaller test tube that you have in your kit, what is that volume? Okay, I know what 10 milliliters look like. I know what 10 milliliters look like. I know what 50 milliliters look like. Okay, this one's between 10 and 50. I'd say it's about 25, 28 milliliters, something like that. If you got a smaller graduate test tube, then you're going to say maybe it's about 8, maybe it's about 7 milliliters. But again, you're guessing. You're not going to say, oh, it's 8.57. If you write 8.57, it's going to be marked wrong because you're putting more precision than your estimate. Your estimate at best is going to be within 1 milliliter, if that. So please keep that in mind. The whole idea of having these things right here, estimate, is again to give you a sense of how large these metric measurements are, to put it in context. Okay. Then this part right here, you have, instead of these right here, the diameter, that'll be just the side. One side is going to have that. And then in order to take the volume, remember for a cube, it's the length, the width, the height, they're all the same. So you're just taking one side and then you're cubing it. Okay. In terms of the, don't use this formula because this formula is incorrect. Before this semester, the only thing the lab tech had were marbles, and we needed you guys to measure the density. So the marbles, of course, is a sphere. This is the equation for the volume of a sphere. We're doing something more simple in terms of the geometric, the geometry of our device. It's a cube, and a cube's volume is the length, the width, and the height. So ignore this. I need to correct that. Okay. The displacement is the same. You know what the initial is, you know what the final is. By difference, by subtracting, you get the volume of the solid. And now you can take the mass, which is going to be the same for both, and divide it by the volume. And you guys are going to be able to tell me what that density is by volume and by direct measurement. Okay. And they should be close, but not exact. So once you fill this out, then you're done. Okay, you're done. Make sure you take photos along the way based on what the direction has. Take a picture of this, upload it, and you're done with this part. Now let's go to the last part. This is your post lab. This is also in your lab manual. Let me go to module here. Okay. And this is where you put everything in context. And this is a post lab. It's more calculations. But basically you're writing, yeah, explain why the two densities varies. I think I told you that already, but you need your own words to do that. Okay, based on the measure density, tell me what color you have. Take a look at that chart that gives you the different density, and then do the percent error. The percent error is going to be the true value. That's what you think it is. Okay, in the chart, in the chart, you have acrylic, which is 1.19 density, cellulose acetate, which is 1.28, glass, which is 2.21, glass common, which is 2.6. One of these will be the correct material for your cube. So let's say that I pick granite 2.7. Okay, let's just for the sake of argument, that's my true value. My experimental value is what I read my experiment is. So I take my true minus my experiment, that difference. Let's say that the granite's 2.7, and let's say I measure this at 2.5 or 2.5. 2.7 minus 2.5 is 0.2, and then I divide by 2.7, the true. So it's the difference between the true and the experimental. I think I have this in your lab manual, divided by the true. So 2.7 minus 2.5, take that difference divided by 2.7, because that's the true, times 100. That's my percent error. Okay, I just want to see how far you are. Then in these right here, this is where you start taking each of your measurements and converting it to different units. Okay, first of all, tell me how many milligrams equals 1 gram. You guys should know that off the top of your head. A milligram is small, so it takes many milligrams to equal 1 gram. How many grams is equal to a kilogram? A gram is smaller than a kilogram. It takes many grams to equal 1 kilogram. And then you need to look this up. How many pounds equals a gram, or how many grams equals a pound? You want the conversion factors up here because you want to use the mass of the cube. This is a cube now. Put it right here, and then convert that grams to milligrams, convert that grams to kilograms, and convert that grams to pounds. I want you to practice dimensional analysis using conversion factor. Then you have the beaker. You have the mass of the beaker. Convert that mass of the beaker in grams to milligrams, convert it to kilograms, and convert it to pounds. And then for one of these, the cube, show how you worked it out using dimensional analysis. Okay, I want to see that work. And then you do the same thing here for length. You know the side of the cube. You know the side of the cube. We said it was like 1.43. Okay. So you know what is? Convert that to millimeters. Convert that to meters. Convert that to inches. Put the conversion factors out here. And then we also know the circumference of the 400 Mil Grad cylinder. That's where I wrap the string. And I want you guys to convert that from centimeters to millimeters, from centimeters to meters, from centimeters to inches, and then show one calculation. The reason why I want you guys to show the calculation is I really want you guys to practice showing how the units cancel. That's the whole idea of dimensional analysis. And then you have your last one here. You've got your 10 Mil Grad cylinder and your 100 Mil Grad cylinder. Convert that milliliter to liters, convert that milliliters to gallons for both. Okay, and then you're done. That's basically it. So you got to have the data before you can do the post lab. But the idea of the post lab is to have you guys convert those measurements to different units. Okay. So when you file your report, there's going to be a part where you have to put in the pictures with the data. Okay, don't put it in your post lab. It's part of your data right here. So when you take this and you upload it to Canvas, then upload not only this sheet, but also upload the photos that you've taken, and everything should be fine. So that's experiment number 2. It's an important experiment. It's an important experiment. Why? Because this is a 50-point lab, but it's also a 25-point lab practical in your midterm, and it's a 50-point lab practical in your final. So it's an important lab. Okay. Are there